Hi children, this is S. Raji going to teach you Coulomb's law. Okay, so today I am going to talk about your Coulomb's law. So what is this Coulomb's law going to give? This Coulomb's law is going to give you the magnitude of the force between two charges. Okay, the two charges can be, both of them can be a positive charge, or both of them can be a negative charge, or one can be a positive charge and another one can be a negative charge. Okay, right? So you know now that if both the charges are positive or both the charges are negative, there will be a force of repulsion, and if one of the charge is positive and the other charge is negative, then there will be a force of attraction between those two charges. Okay, right? So Coulomb's law is not going to tell you whether, it's not going to bother whether the force is attractive or repulsive, right? So whatever it is going to give you the magnitude of the force between two charges. The force can be a repulsive force or an attractive force. So for both the type of forces, it's going to hold good only. Okay, and we will be talking only about point charges, children. Okay, what do you mean by point charges? Charges whose linear dimensions are such as area or volume. Okay, linear dimensions such as area or volume of the charges will be very, very smaller when compared to r. Okay, what is this small r, children? The small r is the distance of separation between the charges. Okay, right? So we are going to talk only about the point charges, for the charges whose linear dimensions such as area or volume will be very, very less when compared to the distance of separation between them. Okay, right? So the amount of charge can be of 10 coulomb also, right? 10 coulomb, two 10 coulomb charges can be separated by a very large distance of, say for example 100 meter. Then those two charges can be considered as a linear charge. Okay, right? Because the linear dimensions will be very, very small when compared to the distance of separation between the two charges. Okay, right? Now let us consider two charges, children. This is Q1 and Q2, right? This is Q1 charge and this is your Q2 charge. Okay, the distance of separation between them, or else the distance between the centers of the two charges, let us consider it to be equal to small r. Okay, now say for example that both the charges are positive charges. Okay, both of them are positive, means you now know that this Q1 will be repelling Q2 along this direction, and this Q2 will repel this Q1 along this direction. That is, the force of repulsion between these two charges will be along the line joining the two charges. Okay, right? This one Q1 will repel this Q2 along this line. That is, this is along the line joining the two charges, and similarly this Q2 will repel Q1 along this line, that is along the line joining the two charges. Okay, the force will be always along the line joining the two charges, right? So now according to Coulomb, the force of repulsion between these two charges is found to be directly proportional to product of the magnitude of the charges. Okay, right? So Q1 and Q2, we are not bothered whether it is plus Q or minus Q, children. It is telling you that it is directly proportional to the product of the magnitude of the charges. Okay, so Q1 into Q2, and it is found to be directly proportional to 1 by r square. Okay, what did I tell you? Directly proportional to 1 by r square, or else you can also say it as inversely proportional to r square, right? So F is, according to Coulomb's law, the force of attraction or repulsion between these two point charges is found to be directly proportional to the product of the point charges and inversely proportional to the square of the distance between the two charges. Okay, now let's combine these two together and write it into a single equation, that is F is directly proportional to Q1 Q2 divided by r square. Okay, right? Now we know that we don't want any mathematical equation to be in the form of a proportionality symbol. We want it to be in an equal to symbol. So for that we multiply it with a constant here, that is the constant of proportionality here is k. Okay, so k into q1 q2 divided by r square. Okay, and what is the value of k here, children? K is found to be equal to 1 by 4 pi epsilon naught. Okay, what's the value of k here? K is equal to 1 by 4 pi epsilon naught. Okay, let this be the first equation, and let me tell you something about this constant of proportionality, that is k equal to 1 by 4 pi epsilon naught, and then we will come back to the Coulomb's law. Okay, so from the SI unit of system, in SI unit, k value is found to be equal to 1 by 4 pi epsilon naught. Okay, and what is this epsilon naught, children? Epsilon naught is called as the permittivity of free space. Okay, and this epsilon naught is a constant value, and this constant value is found to be equal to how much? 8.854 into 10 to the power of minus 12 c square n power minus 1 m power minus 2. Okay, so the value of epsilon naught, that is permittivity of free space, is this much. Okay, this you will have to remember because we need it for doing your problems and all. So only if you remember by heart we can do the problems. Okay, right? And the unit also you will have to know it. Okay, only if you know the unit we can go for the dimensional formula. Now first of all let me tell you what is permittivity, and then we will come back again to the unit, value, dimensional formula, everything of a epsilon naught. Okay, so what do you mean by permittivity, children? Permittivity is nothing but flexibility of the medium to allow the electric field. Okay, what do you mean by permittivity? Permittivity is the flexibility of a medium to allow the electric field. Okay, we are all talking about charges only. So around those charges there will be a field, and the flexibility of a medium to allow that field is called as the permittivity. Okay, right? And permittivity of free space is nothing but the flexibility of the free space or vacuum. Okay, free space or vacuum to allow the electric field lines, right? That's what you mean by permittivity. And how is this unit, children? How did permittivity get this unit? See, now if I substitute in the Coulomb's law, then what will I write? F is equal to, instead of k I can substitute 1 by 4 pi epsilon naught q1 q2 divided by r square. Okay, now I need the unit for epsilon naught only, right? So for that, how can I change it? How will I write it? So what did I write in the last page? F is equal to 1 by 4 pi epsilon naught q1 q2 divided by r square, right? So I am going to write the unit for epsilon naught. So let me take epsilon naught to that side and bring f to the denominator here, right? So q1 q2 divided by r square. So 1 by 4 pi is a constant, so it will not have any unit, that you know. And what is the unit for force, children? The unit of force will be equal to how much? Newton, right? The unit of force is Newton. So force is in the denominator, so Newton will also be in the denominator. The unit of charges is, you know now, that is Coulomb, right? So Coulomb into Coulomb divided by r square. R square is your distance. So distance means meter square, right? So what is its unit? C square. The units in the denominator will go to the numerator as n power minus 1 m power minus 2. Okay, so this is how we are writing the unit for the epsilon naught, that is permittivity of free space, right? So what is the unit for permittivity of free space? C square n power minus 1 m power minus 2. Don't worry, children, by the end of the first volume you will start remembering the value of epsilon naught as well as the unit for epsilon naught and the dimensional formula for epsilon naught by yourself. You will not have to do all these things in your examination or in your test papers which your school teachers are giving you. Okay, right? So you will start remembering all these values by yourself, right? So don't worry about that. So thus we have written the unit for epsilon naught. Now what we have to do? We have to write the dimensional formula for epsilon naught. Okay, right? And what will be the dimensional formula for epsilon naught? So by the side itself I will write the dimensional formula. So again 1 by f, right? So 1 by 4 pi doesn't have any dimensions. 1 by f, right? So what's the dimensional formula for force? Epsilon naught is equal to, what's the dimensional formula for force? Dimensional formula for force will be equal to how much? M L T power minus 2. Okay. And what is the dimensional formula for charge, children? Charge we know, no? That is I is equal to Q by T. This you would have learned in your 10th standard itself. So from this, what is Q is equal to? Q is equal to I into T, right? And what's the dimensional formula for current? Ampere. And what's the dimensional formula for time? That is T. Okay. So AT, right? So for this Q1 I have written AT, and this for this Q2 I have written AT separately like this, right? Then divided by R square. R is nothing but the distance of separation between them. So the dimensional formula for distance is L square. Okay. So what will you be getting? M. So what will you be getting, children? A square, right? A into A square, T square, the whole divided by M L cube T power minus 2. Okay. So let's take this denominator to the numerator. So what will you be getting? M power minus 1, L power minus 3. This T power minus 2, when it goes up, it will become T power plus 2. So T power plus 2 into T power plus 2 will be equal to T power plus 4. T power plus 4. So M has been taken up, L has been taken up, T has been taken up. What else is remaining? Ampere is remaining, right? So ampere square, right? So this is the dimensional formula for permittivity of free space. Okay, right? So this also you remember it. I am just teaching you how to write the dimensional formula, but this you know from your 11th standard itself how to write the dimensional formula, right? So sometimes you might not be remembering these dimensional formulas and all. In case you don't remember it, if you have time, what you can do? You can just work out, right? Units also you can work it out like this, and dimensional formula also you can work it out like this if you have time. Okay, right? But believe me, you will start remembering all these things by yourself at the end of this volume. Okay, so don't worry about those things and all, right? So let's go back to our Coulomb's law, children. So where did we stop with the Coulomb's law? So according to Coulomb, the force of attraction or repulsion between the two charges is found to be equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square. Okay, right? So now this is your Coulomb's law, and the unit for force, you know that it is Newton, right? The unit of force is Newton. Now we are going to define 1 Coulomb with the help of this Coulomb's law. Okay, right? We are going to define 1 Coulomb, right? For defining 1 Coulomb, let us consider that this Q1 is equal to Q2 is equal to 1 Coulomb, and the distance of separation between the two charges to be equal to 1 meter. Okay, right? So now what will happen to the force, children? That force F will become equal to 1 by 4 pi epsilon naught 1 into 1 divided by 1 square. Okay, 1 into 1 divided by 1 square, and what this will be equal to? 1 by 4 pi epsilon naught. Okay, now substitute the value for epsilon naught. 1 by 4 pi into epsilon naught value. Now you know that it is equal to 8.854 into 10 to the power of minus 12. Okay, right? Minus 12, right? So substitute all these values, children. After substituting all these values, you will find the force F to be equal to 9 into 10 to the power of 9 Newton. Okay, 9 into 10 to the power of 9 Newton. Okay, right? So from this, we are going to define 1 Coulomb. Okay, right? So how can you define 1 Coulomb? 1 Coulomb is the amount of charge. Okay, 1 Coulomb is the amount of charge that repels an equal and similar charge. See, if Q1 is equal to 1 Coulomb, then Q2 is also equal to 1 Coulomb, right? So they both are similar charges. Okay, right? They are both are similar charges, and they both are equal charges also, right? So 1 Coulomb is the amount of charge that repels an equal and similar charge with a force of 9 into 10 to the power of 9 Newton, okay, when placed in vacuum, right? Epsilon naught value is in vacuum, for vacuum, right? That is your free space, right? When placed in free space or vacuum at a distance of 1 meter between them. okay, at a distance of 1 meter between them. This will be the value of 1 coulomb, okay, right. So when can you say, I will tell you once again, when can you say that the charge is equal to 1 coulomb, children? When 1 coulomb is the amount of charge, right, that repels an equal and similar charge, right, equal and similar charge with a force of 9 into 10 to the power of 9 Newton, okay, when placed in vacuum or free space at a distance of 1 meter from it, right. Then you can say that the charge is equal to 1 coulomb, okay, right. So this is in SI unit. Again, this 1 coulomb is a very large amount of charge, children, right. For us, if you say, if you ask 1 is greater or 100 is greater, we will be saying that 100 is greater. But in physics, this 1 coulomb, the 1 coulomb charge is a greater value of charge. It's a greater value of charge, okay. It is difficult for us to handle this amount of charge and all. For us, it can be 1 is a smaller value, but in physics, this 1 coulomb itself is a larger value of charge, okay, right. So in physics, we will not be going for 1 coulomb and all. Instead of 1 coulomb, we will be using millicoulomb, okay, the smaller units of charges. Okay, smaller units of charges like millicoulomb. Millicoulomb means how much? Milli means 10 to the power of minus 3 coulomb, and microcoulomb. Microcoulomb means how much, children? 10 to the power of minus 6 coulomb, and nanocoulomb. Okay, nanocoulomb means 10 to the power of minus 9 coulomb. Okay, right. So again, I am telling you, 1 coulomb is a greater amount of charge. Okay, right. So we won't be coming across 1 coulomb and all, but in problems and all, for making it simpler, okay, they will be giving it as 1 coulomb, 2 coulomb, 6 coulomb, 8 coulomb and all. But remember, it is of a greater value, children. So practically speaking, 1 coulomb of charge will not be using. We will be going for smaller units of charges only, that is millicoulomb, microcoulomb and nanocoulomb, right. And I have written you the values of milli, micro and nano below, right. You can use it. Okay, children, right. So this is about your Coulomb's law. Now we are going to talk about Coulomb's vector form. Okay. So hope you have understood up to this. Okay. Now we are going to give the vector form of your Coulomb's law. Okay, right. That is, we are going to consider the direction of that Coulomb's force also. That's what you mean by Coulomb's vector form. Okay, right. So again, the same charges we are going to consider, children. Q1 is one charge and Q2 is another one charge. Okay, right. Let the distance of separation between the two charges be equal to R. Okay, right. Now we know that this Q1 will be repelling Q2 along this direction, right. This Q1 will be repelling Q2 along this direction, and in the vector form I write this force on Q2, right. Listen carefully. I write the force on Q2 due to Q1 as F21 vector. Okay, F21 vector, right. So what is this F21? Force on 2 due to Q1. Okay, force on Q2 due to Q1, right. See, this is an inverse U, right. We usually write U as like this, right, but you have to go inverse U, right. You are coming in the reverse direction, right. This is U, right. So what is F21? F21 is the force on Q2 due to Q1. Force on Q2 due to Q1. Okay, right. Similarly, this Q2 will also be repelling Q1 along the line joining the two charges. And how should I represent that forces? See, 2 is acting on 1. Okay, so 2 is acting on 1 is 1, 2. That is 2 is acting on 1, right. Reverse U or inverse U, right. 2 is acting on 1, right. So what is this F12 vector? F12 vector is the force on Q1 due to Q2. Okay, children, right. Now let me talk about this distance. See, usually we take this distance as a vector scalar quantity only, but we can also represent it in the vector form. See, the distance between the two charges Q1 and Q2 is not changing. Its magnitude is equal to R only, right? But when I talk about the force on Q2 due to Q1, I can write the distances R. 1 is acting on 2, right? So 1, 2. Okay. This will be equal to R21, that is 2 is acting on 1. So the distance I am considering it from the second charge to the first charge. Okay. So what is this R12 pa? See, all this will be equal to R only, right? The magnitude of these two distances will be the same only, right? So what is R12? 1 is, when I talk about the effect of force of Q1 on Q2, I measure the distance from Q1 to Q2. So that is R12. Okay, right? R12. Okay. When I talk about the force on Q1 due to Q2, I go from Q2 to Q1, right? So that is 2 to 1. Okay. So the magnitude of those two distances will be equal to R only. Okay. But what will be how will be the direction? See, I have not put any vector notation here, but when I put a vector notation, R12 is equal to R21, right? If I put a vector notation, this is a unit vector notation, right? If I put a vector notation, now you know that what I have written is completely wrong, because there should be a negative sign here, right? So this negative sign shows that if this distance, if this R12 distance is from 1 to 2, this R21 distance is from 2 to 1. Okay. So here we talked only about the magnitude. So what I have written is right, but here when I put a vector notation, unit vector notation here, I have to include a negative sign here, right? Hope you understand this concept, children. This you would have come across in your maths and all, right? So with this, let me write an expression for force on Q2 due to Q1, right? Force on Q2, right? Force on Q2 due to Q1, right? This Q1 is acting upon Q2, right? So what this will be equal to, according to Coulomb's law, 1 by 4 pi epsilon naught Q1 Q2 divided by, what is the distance? How should I take the distance? I am taking it from 1 is acting on 2. So the distance I should take it from 1 to 2, right? So this will be equal to R12 square into R12 unit cap. Right? You know that the value of this R12 is equal to 1 only. So multiplying this equation with this vector, unit vector notation will not change the magnitude of the force. Okay, right? Now similarly, what will be F12 vector? What is F12, children? Force acting on 1 due to Q2, right? Force acting on 1 due to Q2. Okay, so what is this? This is your F21 vector, and what is this? This is your F12 vector. Okay, right? So let me write the expression according to Coulomb's law. That will be equal to 1 by 4 pi epsilon naught Q1 Q2. All of them are the same, but how about the distance? 2 is acting on 1, right? So I am measuring the distance from 2 to 1. 2 1 square R21 unit cap, right? Notice one thing, children. When I write the force, I am writing it as 2 1, and when I am writing the distance, I am writing it as 1 2. Okay, right? Because in your book they have written so only. Okay, right? So but you have to understand, right? If you understand and study, you will be able to remember it. Don't just mug up that is 2 1 1 2 and all. If you mug up like that, it will not help you in any way. So understand and write. Okay, right? So F21 is the force acting on 2, okay, force acting on 2 due to Q1. So I am measuring the effect of force from 1 to 2, okay, and vice versa. For F12, it is vice versa. Okay, right? So now see, let me use this condition here, right? Let me use this condition in this equation. If I use it, what will I be getting? F12 vector will be equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R21, right? Now I have shown here itself that this R21 is equal to R12, right? So instead of R21, let me write R12 square, right? No harm, because all those will be equal to R only, right? No problem. Now instead of R21, what can I write? I will write R12 unit cap with a negative sign. Okay, right? Only if I don't put this negative sign, it will be wrong, right? Now I have used the negative symbol. So this can be rewritten as minus of 1 by 4 pi epsilon naught Q1 Q2 divided by R12 square R12 unit cap, right? And what is this equal to, children? This is nothing but your F21. Okay, right? So this F12 vector is equal to minus of F21 vector. Okay, that is, this is your vector form. Okay, right? And this shows that your Coulomb's law is according to your Newton's third law. Hope you remember your Newton's third law. For every action, there is an equal and opposite reaction. Okay, right? So according to Newton's third law. Okay, right? Here any one can be taken as a reactional force and any one can be taken as a actional force. It's up to us. Okay, right? So whichever one you want, you can consider it, right? So this is the vector form, and from the vector form we have shown that Coulomb's law is according to the Newton's third law of motion. Okay, right? And this Coulomb's law is otherwise called as a central, Coulomb's force is otherwise called as a central force. Okay, right? What do you mean by central force? See, when I talked about the distance between the two charges, I talked it from one center of one charge to the center of the other charge. Okay, right? As it is taken from, as the distance is measured from center of one charge to the center of other charge, it is otherwise called as a central force. Okay, and the range of this Coulomb's force will always be around, okay, will be always be around, range will be 10 to the power of minus 15 meter to 10 to the power of 18 meter. Okay, this is not your gravitational force, this is your Coulomb's force, right? Electrostatic force. So the range will be higher range only, that is from 10 to the power of minus 15 to 10 to the power of plus 18 meter. Okay, right? Now using your Coulomb's law, we can also write an expression for the dielectric constant. Okay, right? So that alone is remaining in the Coulomb's law. So what was the formula for? Now I am going to write an expression for dielectric constant. So what is dielectric constant? That I will tell you. Okay, right? What was the formula for the force between 2 point charges in vacuum or free space? 1 by 4 pi epsilon naught Q1 Q2 divided by R square. Okay, right? And what will be the formula for the force between two charges in a medium? When these two charges are placed in vacuum or air, right? See, actually the value for permittivity is for vacuum only, right? But for air also we will write the same value, because there will not be a much difference in the value between permittivity of vacuum and permittivity of air, right? So that's why we take epsilon naught is equal to 8.854 into 10 to the power of minus 12 to be the value of permittivity of vacuum or air or free space, right? Anything can be said, right? So now this is in Q1 Q2. Okay, the force between them will be F in air, right? Let me write it as air, but you should know it can be air medium, vacuum or free space, right? Anything can be said, right? Now the same two charges, I keep it in a medium, Q1 Q2, I keep it in a medium of permittivity epsilon. Okay, permittivity epsilon. Okay, so in that case the force between the two charges will be written as Fm, right? So what will be Fm equal to? Fm is equal to 1 by 4 pi epsilon Q1 Q2 divided by R square, right? Let this be the first equation and this be the second equation. Now what I am going to do? I am going to divide the first equation divided by the second equation. So what will I get? F air divided by force between the two charges in medium is equal to, see, 1 by 4 pi epsilon naught Q1 Q2 divided by R square divided by 1 by 4 pi epsilon Q1 Q2 divided by R square, right? The charges are not differing, the distance between the two charges I have not changed at all, right? Only thing is, instead of air or free space, I have kept a medium. Okay, right? So what will happen, children? This Q1 Q2 by R square, Q1 Q2 by R square will cancel off. 1 by 4 pi will get cancelled off. And what will I be getting? F air divided by F in medium is equal to epsilon by epsilon naught. Okay, right? And this is equal to K or epsilon R. Okay, right? So this K I'll teach you later, but now let us consider the ratio to be equal to epsilon R. Okay, and what is epsilon R? Epsilon R is the relative permittivity. Okay, and what do you mean by relative permittivity? You are comparing the permittivity of any medium with the permittivity of free space, vacuum or air medium, right? Anything you can say, right? So what do you mean by relative permittivity? We are relative permittivity means comparing the permittivity of any medium to the permittivity of free space, right? So this epsilon R is dimensionless. Okay, right? Because it is a ratio between two similar quantities. No, it doesn't have, epsilon R doesn't have any unit. Okay, right? No unit, and it will not have any dimensional formula also. Okay, right? So epsilon is the permittivity of the medium and epsilon R is the relative permittivity. Okay, right? So remember this formula, that epsilon R is equal to epsilon by epsilon naught. From this you can write epsilon is equal to epsilon R into epsilon naught. This formula we will be using it then and there for your problems and all. And also remember this formula, that is Fn air is divided by Fm is equal to epsilon R. Okay, right? So that's all, children. Only this much has been taught to you in your Coulomb's law. Okay, right? Hope this has been made simple for you. If you have any doubt, you can comment me in the comment section. Okay, right? If you have any doubt, you can ask me. I'll contact you or I'll message you back. Okay, children. Thank you.